Okay, so we're going to get into video number 2. This video we're going to look at solving some exponential equations, and then we'll move into video number 3, which is solving some examples of both exponential and logarithmic equations. Okay, so when we look at example number 7, we have 3 to the 2x power plus 3 to the x power minus 2 is equal to 0. Okay, and we're going to see, like the first 3 examples that we look at, 7, 8, and 9, are all one type of exponential equation that we're solving, and these are exponential equations that are written in a quadratic form. And how do I know these are written in a quadratic form? Well, when I look at the first term, 3 to the 2x power, we know we multiply exponents when we have a power raised to a power. So 3 to the 2x power is equivalent to saying 3 to the x power quantity squared, plus we have 3 to the x power minus 2 is equal to 0. Well, if we do a u substitution here, so if we let u equal 3 raised to the x power, then I can take this exponential equation and express this exponential equation in a quadratic form. So this is like saying u squared plus u minus 2 is equal to 0. Okay, so that's a quadratic equation that is factorable for us. So that's going to factor to u plus 2 times u minus 1 is equal to 0. And that happens when u is negative 2 or u is equal to 1. But we're not done solving this yet because we weren't asked to solve this equation here for u. We were instead asked to solve it for x. So we need to go and replace u with 3 to the x power. So we want to find where 3 to the x power is negative 2 or where 3 to the x power is equal to 1. So if we think about the graph of 3 to the x power, again, we should know that that graph contains 2 points. So 0, 1, and then 1, comma 3. Okay, and then graphically, my curve looks like that. So you should be able to look at that curve and know, hey, that curve is never going to be negative. So 3 to the x power is never going to be equal to negative 2. So there's no solution to that part. 3 to the x power is going to be equal to 1 when x is equal to 0. So that is our only solution to that particular equation. Do we need to check domain of an exponential equation? And the answer to that is no. And the reason being is anytime we look at an exponential function, we know the exponential function has a domain of all real numbers. So we don't have to check domain at the start when solving an exponential equation. All right, let's take a look at number 8. So for number 8, we have 3 to the 2x power plus 3 to the x plus 1 power minus 4 is equal to 0. Okay, so we can approach this very similarly. The first term, 3 to the 2x power, is 3 to the x power quantity squared. When you look at that middle term, 3 to the x plus 1 power, when do we add exponents? Well, we add exponents when we multiply two exponents that share the same base. So that middle term, 3 to the x plus 1 power, we could think of that as being 3 to the first power times 3 to the x power minus 4 is equal to 0. And just like the previous example, we have an exponential equation that is written in a quadratic form here. Okay, so if we u substitute, so if we plug u in the place of 3 to the x power, this equation becomes u squared plus 3u minus 4 is equal to 0. This once again is factorable, factors to u plus 4 times u minus 1. So that product is going to be 0 when u is equal to negative 4 or u is equal to 1. But again, we're not solving the equation for u. We're solving for x. So we're going to replace u with 3 to the x power. So 3 to the x power is never negative 4, so that part has no solution. 3 to the x power is going to be equal to 1, again, when x is equal to 0. Okay, so just so happens that those two equations have a solution of x is equal to 0. That's not always the case for those exponential equations. Okay, let's see what you guys do with number 9. So for number 9, you have 3 to the 2x minus 2 power minus 12 times 3 raised to the x minus 1 power plus 27 is equal to 0. Okay, so if we rewrite number 9, this is like saying 3 to the x minus 1 power, quantity squared, minus 12 times 3 to the x minus 1 power, plus 27 is equal to 0. And again, we can let u equal 3 to the x minus 1 power. So if we do that, this exponential equation we can rewrite as a quadratic equation. All right, so if I do my u substitution, we get u squared minus 12u plus 27 is equal to 0. That equation factors to u minus 9 times u minus 3, which means that u is equal to 9 or u is equal to 3. Again, though, we are not solving the equation for u, we are solving for x. So we're going to replace u with 3 raised to the x minus 1 power is equal to 9. And 3 raised to the x minus 1 power is equal to 3. Okay, so we can solve both of these equations using our rule for solving exponential equations. So we get 3 to the x minus 1 power is equal to 3 squared for the first one, which means x minus 1 is equal to 2, which means x is equal to 3. And then for the second equation, that's like 3 to the x minus 1 power is equal to 3 to the first power, which means x minus 1 is equal to 1, and x is equal to 2. Okay, so those are our two solutions for number 9. All right, on to number 10. So for number 10, we have 3 raised to the x power is equal to 14. So this is going to be kind of like similar to our second type of exponential equation that we need to solve. Okay, so when we think about exponential equations, like our rule was to try to get both sides of the equation written as an exponent that shares the same base. And we're not going to be able to do that in this particular case because I can't write 14 as 3 raised to some power. Do I know the approximate value of x? I would say yes. X is going to be somewhere between the integer values of 2 and 3 because 3 squared is 9, 3 cubed is 27, and 14 is somewhere between 9 and 27. But we don't know exactly what x is going to be equal to. Okay, so one way of working this out is to take this exponential equation and rewrite it in log form. So if we want to rewrite this exponential equation in log form, the exponent of base 3 is equivalent to the log base 3. We are taking the log base 3 of 14, and that's going to be equal to our power x. Okay, so that's a really simple, easy way to solve that equation. But it's not going to be the way that I recommend that you guys solve these equations. Okay, the way that I'm going to recommend that you guys solve these equations is to take your original exponential equation, and we are going to take the natural log of both sides of this equation. And in doing so, like ultimately we are trying to solve for the variable x. Well, we can take this variable x now because we've taken the natural log of the left-hand side, and I can pull that exponent out front as a factor. So this gives me x times the natural log of 3 equal to the natural log of 14. And now I can solve this equation for x by dividing both sides by the natural log of 3. Well, when you look at these two solutions don't look alike, but they actually are the same, because if I use the change of base formula for my solution on the left and rewrite the log base 3 in terms of natural log, we would do that by taking the natural log of the original argument and dividing that by the natural log of the original base. Okay, so the solution that you came up with on the right is just the change of base formula essentially for the solution that we came up with on the left. Okay, now my preference, I would prefer you guys working through the examples like I did on the right. I think generally speaking, that's the better approach for you to take when solving equations of that type. Okay, so let's do some more challenging examples of these types of exponential equations. Okay, so for number 11, we have 2 raised to the x plus 1 power is equal to 5 raised to the 1 minus 2x power. Okay, so again, we have the same problem that we ran into in the previous example, is I can't rewrite both sides of this equation as an exponent that shares the same base. Okay, I'm not going to be able to find a base for 2 and 5 that are going to be the same. Okay, so I'm going to do what I did in the previous example. I'm going to take the natural log of both sides. When I do that, I can then pull the exponents for both out front as factors. So we get x plus 1 times the natural log of 2 equal to 1 minus 2x times the natural log of 5. And then I want to solve this equation here for x. So the way I'm going to do that is I'm going to distribute the natural log of 2 across both terms on the left, and the natural log of 5 across both terms on the right. Okay, and then if I want to solve for the variable x, I'm going to do like we did in the section on inverse functions. I'm going to move all x terms to one side, terms without x to the other side. So we get x ln of 2 plus 2x ln of 5 equal to the natural log of 5 minus the natural log of 2. And then I can factor an x out of the left-hand side. And then divide. So we get x equal to the natural log of 5 minus the natural log of 2 over the natural log of 2 plus 2 ln of 5. Okay, and that's going to be your solution for that equation. Okay, if you got this as a solution, is that solution legit? And the answer is yes. If at this step here, instead of moving our x terms to the left-hand side, we moved our x terms to the right-hand side, and the terms that did not have an x to the left-hand side, and then isolated x, you would have gotten that solution in red. Okay, is this solution legit? And the answer is yes, because we could take our log properties. Because we're subtracting two logs that share the same base in the numerator, we can divide or combine into a single log by dividing their arguments. And then on bottom, because we're adding two logs, I can combine into a single log. So 2 ln of 5 is like saying the natural log of 25, and when we have the natural log of 2 plus the natural log of 25, that is equivalent to the natural log of 50. Okay, so there are 3 potential answers that you could have come up with when solving number 11. Okay, I'm going to have you guys give number 12 a try. Okay, so number 12, similar to number 11, just I made things a little bit more complicated for number 12. Okay, so you have e raised to the 3x power equal to 10 raised to the 2x power times 2 raised to the 1 minus x power. Okay, so we're going to use the same approach that we did in the previous example. We're going to take the natural log of both sides. Okay, so when I take the natural log of the left-hand side, that's going to wind up simplifying to 3x. And then I'm taking the natural log of a product on the right-hand side. So I can separate that into the natural log of the first factor, which I'm going to take 2x and pull it out front as a factor, plus the natural log of 2 raised to the 1 minus x power. And once again, I'm going to take that exponent 1 minus x, pull it out front as a factor. Okay, so I'm going to distribute the natural log of 2 across these two terms. So we get 3x equal to 2x ln of 10 plus the natural log of 2 minus x times the natural log of 2. And then I'm going to move all the terms that have x in them to the left-hand side. So we get 3x minus 2x natural log of 10 plus x times the natural log of 2 equal to the natural log of 2. And then if you guys don't mind, I'm going to combine two steps in one. So I'm going to factor an x out of the left-hand side and then divide. So when I do that, we get x equal to the natural log of 2 over 3 minus 2 times the natural log of 10 plus the natural log of 2. Okay, so that's going to be your solution for that one.